Review problem number 2, more 2D kinematics. In this one, we again launch an object, I think it's a ball this time, from an initial height. What's different from problem 1 is that this is thrown at an angle. This angle here is below the horizontal, so you're throwing the ball slightly downward from some initial height. Now the problem tells you the initial speed, and it also tells you the time to hit the ground. It doesn't tell you what this initial height is. That's something we'll figure out over the course of the problem. And we're given the angle. Okay, so as in problem 1, we're going to set this up. We'll list the initial positions. That's assuming a coordinate system where the origin is directly below where the ball is launched from. So x initial is going to be 0, and y initial is this mystery height, y0. Now we need the initial velocity components. If we look at our velocity vector, and consider it to be the hypotenuse of a right triangle, then Vx initial is the adjacent side of that triangle, Vy initial is the opposite side of that triangle. So we have Vx is Vi cosine theta, Vy initial is Vi sine theta, because it's opposite. And keep in mind that the y component is going to be going downward, and so in our coordinate system, that gets a negative sign. Now we can write the position components as a function of time. That's kinematic equation number 3. And we plug in what we know. X initial is 0. There's no acceleration in the x direction for projectile motion. So that's just V initial cos theta times time. And in the y direction, y initial plus V y initial t plus 1/2 ay t squared. That equals a bunch of stuff. Our mystery height y0, our initial y velocity Vi sine theta times t, and 1/2 negative g t squared. So the problem is set up now. Now we can answer these questions. Question D, how far does the ball travel horizontally when it lands? So here's the path of this ball. And we want to figure out what that distance is along the x-axis when it lands. And again, we can use our problem-solving procedure. We're given a whole bunch of stuff. We know x initial is 0. We don't know y initial. This quantity is unknown to us still. We know Vx initial. We know Vy initial. We know Ax. We know We also know the time to hit the ground. In fact, that's going to make our lives way easier. We want to find x final, or x final when the ball hits the ground. And there are several ways you could do this. They all boil down to the same thing. You could use either the second or third kinematic equations for x. And if you don't believe me, go through your list of 8 kinematic equations. See which ones are going to work for you. So let's just use kinematic equation number 3 because that's my favorite. Easy. Those things are both 0, just like we said over here. And all we have to do is plug in these values. We know v x initial because we calculated it over here. You've got all these numbers. And we know t. That was given in the statement of the problem. So just plug it in and there's your answer. Part E, what was the initial height, y0? All right, so once again, we have a bunch of given quantities, got a bunch of stuff there. We want to find that initial height, y0, and there are there's just one equation we could use. And again, it's our favorite one. Put in the values that we know. Got all of this stuff because that t is still the same t that we were given, the time to hit the ground. So we know all of these numbers and we just solve that for y0. This problem was being kind of nice to you by giving you this value t, because usually that's the hardest thing to find in kinematics problems. But just when you thought that the problem was 100% nice, in the very last question, they do ask you to solve for t. And unfortunately, the only way to do it is to use the quadratic formula. So after some parts that weren't so bad, now part F is pretty horrible. We're asking now, what's the time that it takes to reach a height 10 meters below where the ball started from? So, again, we're given a bunch of stuff. We now want to find this new value of t for the scenario where the ball's 10 meters below its starting point. And again, if you look through all of those equations, you'll realize that the only one that can do the job is this one. And unfortunately, none of these terms go away. They're all non-zero. so we have to do some algebra and the quadratic formula. So I'm going to keep all these symbols as I've written them here right now, and do the algebra and the quadratic formula, and then at the end I'll plug in these other expressions we found for each of those symbols. So here's the little bit of algebra where I'm just rearranging this equation. And we identify that as A, this is B, this is C. Oops, that's T squared. So that the quadratic formula looks like T equals opposite B plus minus square root B squared minus 4 times A times C, all divided by 2 times A. And now, just to make things look extra horrible, I'll put in the expressions for each of those. Vy initial was negative V initial sine theta, so that is V initial sine theta. There it is again. Because this is squared, that minus sign doesn't matter. And negative 4 times 1/2 is negative 2. A is negative G plus 2G. Y initial minus Y final is going to be 10 meters. Right, because the problem is asking for what happens when the final position is 10 meters below the starting position. So if we started at 100 meters and ended up at 90 meters, then the difference would be 10 meters. And 2 times 1/2 is 1, A is negative G. Alright, so that's kind of horrible, but that's the answer. I didn't put in any numbers along the way. If you put in numbers along the way, then maybe you wouldn't have an expression that huge. Keep in mind that this will give you 2 values. You need to use the positive value because it only makes sense for positive time. It can't hit it can't be over before it started or something. And again, I could maybe ask you some conceptual questions about this problem, like explain your problem-solving method, explain the steps you took to figure out parts D, E, or F, explain why the horizontal velocity is constant, explain why the vertical velocity changes. I could ask you to calculate other stuff, like some of the things we did in problem 1, for instance. What is the final velocity vector when the ball hits the ground? Or what's the final velocity vector at this time after it falls by 10 meters? So be prepared to do all those types of kinematic calculations. Maybe a problem that combines the questions from problem 1 and problem 2 together.